So students, welcome to a new session of micromechanics. In this session we will see the concept about strength of material approach and find out longitudinal Young's modulus and stiffness stiffness using micromechanics concept. So according to this strength of material approach, so you see, let's see, this is a composite. Now there is a fiber inside, there are multiple fiber in a particular composite. So let's take a one single fiber of thickness TF as shown in the figure. Now the total thickness of the composite is TC. So the matrix, each of this matrix will be Tm by 2 because both side is there, so Tm by 2. Let's take this matrix. So what is the area of fiber? So if the height of the composite is h throughout this matrix as well as the reinforcement, then what is the area of this fiber? Tf into height. This Tf into this h. So area of fiber is Tf into h. Similarly, what is the area of matrix element, what are the present in this section? So Tm, so Tm by 2, Tm by 2, so Tm multiplication of h. So here area of matrix will be Tm by h. So if we will consider this total as Tc, that is thickness of this composite, then area of the composite will be Th in Tc into h. So now what is the volume fraction of the fiber? As you know in the previous session, volume fraction of the fiber is F by AC. So F by AC here is nothing but your, if h is equal in both terms, so this Vf can be written as Tf by Tc, thickness of the fiber by thickness of the composite. Similarly, volume fraction of the matrix will be Am by Ac. So you put these values of Am and Ac here, it will be Tm by Tc. It can be noted here, this Vm, this volume fraction of the fiber will be equal to 1 minus Vf, volume fraction of the matrix will be equal to 1 minus Vf, that is volume fraction of the fiber. Now here, so we saw here what is the, let's say for this particular, we will see this particular theory, we will enlarge this view. Now you see this in this figure, sigma c, so this is one direction or your longitudinal direction. So in this direction, let's sigma c, sigma stress value is there, stress value is applied, is registered or informed through this material. If you will see, then let's say this longitudinal stress, this sigma c is nothing but a longitudinal stress in this direction. Let's consider this as your transverse direction, which we will see in our next session. So this sigma c, if longitudinal stress applied to the representative volume element to calculate here longitudinal Young's modulus. So we will see how to calculate the longitudinal Young's modulus. Now if we will see the force on this, so sigma c stress is there, so stress is nothing but force per resistive force per unit area. So this force upon this composite will be equal to the summation of force on the fiber with force of the matrix. Now Fc, as you know, sigma is nothing but sigma, so sigma is F by A. So this force will be sigma c into cross sectional area. So here we will see sigma Fc is nothing but sigma c into AC. Similarly, force on this fiber, sigma F into F, and let's see this Fm, that is nothing but force exerted in the matrix, will be equal to sigma of the matrix into Am. So as we know, our stress is directly proportional to strain. If this proportionality symbol, then it will be E into epsilon. E is nothing but your Young's modulus, or we can say elastic modulus, and epsilon is strain. If longitudinal stress is acting, it will be linear strain. Now see, use this concept here, then sigma c will be composite, the stress, longitudinal stress will be equal to E1 into strain for the composite. So this elastic modulus is nothing but our longitudinal elastic modulus. Okay. Now similarly, this sigma F will be EF epsilon F, and sigma M will be EM epsilon M. This EF, EM are the elastic modulus of the fiber and matrix respectively. Similarly, this epsilon F and epsilon M are the strain for the fiber and matrix respectively. Now let's put this value in this equation. What we will see? Epsilon 1, put this value, so Fc is nothing but sigma c AC, and sigma c is nothing but E1 epsilon c. So Fc will be E1 epsilon c AC, which will be equal to EF epsilon F area F addition EM epsilon M area of matrix. So these are of fiber, these are of matrix. So in this longitudinal, as you see in this figure, to make this matrix stable, the strain applied on this section will be equal to, strain applied on the matrix will be equal to composite as well as the final matrix. So we will see, you put this value, then EC cancel epsilon in all these terms, it will be remain E1 will be equal to E1 epsilon is C, if E1 AC, you cancel these terms from this equation, it will remain E1 AC plus will be equal to, so I am writing here E1 will be E1 AC will be EF F plus EM M. Now divide AC, divide this AC, divide AC in this equation, we will get E1 will be equal to EF F by AC plus EM M by AC. So finally we know this AF, area of the fiber by area of the composite, is nothing but volume fraction of the volume fiber fraction or fiber volume fraction, and AMAC will be your matrix volume fraction VM. So finally we got our longitudinal elastic modulus. When a longitudinal stress is applied on a composite, E1 will be EF VF plus EM VM. EF and EM are the elastic modulus of the fiber and matrix. Similarly, the VF and VM are the fiber volume fraction of the fiber and matrix respectively. So finally we got E1 will be equal to EF VF plus EM VM. Now this is one particular graph between fiber to composite load ratio with fiber to matrix moduli ratio. So graph between F by FC, here EF by EM. So thanks for this session. We will meet you in another session.